Namaskara. We will continue our discussions on Bellman and Ford algorithm. We have defined the class of walks W I, okay, the set of all walks from S to V with at most I edges. Alpha I is the weight of the minimum walk, alpha I V is the weight of minimum walk in W I, it is V, it is depending on V. So, these alpha i's are satisfying certain interesting properties if G has no negative cycle, if G has no negative cycle, then alpha I V equals minimum over U not equal to V of alpha I minus 1 U plus weight of U V. Not only this, we have alpha n minus 1 U equal to delta n minus 1 U, which is equal to delta U. For all vertices this is true. These two properties allow us to write the following program that would start from alpha 0, then in one iteration we will build alpha 1 for all vertices, and finally we stop at alpha n minus 1. So, here is the code for this: Bellman Ford. This takes the directed graph V E, weight function W, source S, and G has no negative or zero cycle, and we are going to use an array. This is like a pseudocode. So, we are going to use an array. This array is D array. D I V is supposed to hold alpha I V. The purpose of this array D is to hold this value. So, we have to compute in our code the values DIV. Since our goal is to have alpha IV, the alpha IV based recurrence is used for the computation of the D values. Okay. So, I initialize D0V to alpha 0V for all V. So, this is the first step. In the first step, D0S is 0 and D0V is infinity for all V belonging to V minus S, V minus the small s. Okay. So, you have initialized. Now, second step will be the for loop. You have to compute
bigger font. Hereafter you can start bigger font.
No, this itself I can clear.
From here, yeah.
Start from point 2, sir.
Yes.
Start from point 2.
Yeah.
Continue.
For I equals 1 to n minus 1. So, I am going to compute when I equal to 1 D1 array, for I equals 2 the D2 array, and so on. Okay. So, for I equals 1 to n minus 1, di di v equals di minus 1 v, di v is di minus 1 v, and then we are going to check for each u v in E if, this is the condition we are going to check, if d IV is greater than d I minus 1 u plus weight of uv, then we are going to update this, d IV is equal to d I minus 1 u plus weight of uv and parent of v is u. Okay. So, when we do this n minus 1 times, we get third step, return d n minus 1 v for all v belonging to v. Comment d n minus 1 v is delta v, the weight of the shortest path is obtained. Okay. Straight away all I have done is that implemented that. The cyclic dependency is broken by the alpha values. Cyclic dependency was there for the delta values. So, I created a new class where we can go smoothly in a single direction and obtain the values that we want. So, this is called the iterative method. The values that you want to obtain is to be obtained by solving an equation. Since we cannot solve that equation, we use the relation to iteratively and converge to the answer we are getting. We are reaching our answer in n minus 1 stages. Okay. So, this is valid if G has no negative cycle. What happens if G has a negative cycle? If G has a negative cycle, we can still do these computations. The D arrays will have some values, but those values may not represent the weight of the shortest path. They are just some numbers, that is it. Okay. Therefore, you should not output. You should not output the D array value, Dn minus 1 array value if G has a negative cycle. But how do we know whether the G has a negative cycle or not? The input can be an arbitrary graph. If the input has no negative cycles, if we know that, we can straight away run this code, because we know G has no negative cycle, we know this kind of computation will lead to the answer. So, there is no issue if G has no negative cycle. But if you have no idea whether G has a negative cycle or not, you can still do this computation and then you can detect using the Dn minus 1 values whether G has a negative cycle or not. That is the beauty of this method. Okay. The Dn values can be used to check whether G has a negative cycle or not. Here is the property of the values in Dn minus 1 array. Okay. So, theorem, if G has no negative cycles or 0 cycles, we know that the delta V values satisfy Bellman equation. Delta V is less than or equal to delta U plus weight of UV. This we know. For all U, we know that this is Bellman equation. If G has no negative cycle, we know that delta V is nothing but delta n minus 1 V and delta U is delta n minus 1 U plus weight of UV. And if G has no negative cycle, we know that delta n minus 1 is nothing but alpha n minus 1 V is less than or equal to alpha n minus 1 U plus W U V. But alpha n minus 1 values are in the D array in our program that we have in the pseudocode. That means D n minus 1 V is less than or equal to D n minus 1 U plus weight of U V. So, look at the condition that we have derived. If G has no negative cycles or 0 cycle, if G has no negative cycle or 0 cycle, Dn values satisfy this condition. So, the negation of that, the contrapositive, what is contrapositive? If P implies Q, not Q implies not P. Okay? Not P implies, not Q implies not P. I will write it as not here also. So, the contrapositive of what we have proved is the following. If there is an edge UV such that D of n minus 1 V is greater than D of n minus 1 U plus weight of UV, then G has a negative cycle. Okay? If there is a UV such that D n minus 1 V is greater than D n minus 1 U. So, look at this implication. This implication shows that I can check whether G has a negative cycle or not. Therefore, compute up to Dn minus 1, then you just check whether there is a negative cycle or not. If there is a negative cycle, simply say that G has a negative cycle. Do not return the D values, because D values do not hold the shortest path weights. D has some numbers, that is all. Okay? But if G does not have a negative cycle, we know that D has the correct value, you can return it. Therefore, this is the way to deal with arbitrary graph. Okay? If G is an arbitrary graph, that is, it may have positive cycle, negative cycle, 0, it can have anything. It really does, it just a weighted graph is given. Okay? When a weighted graph is given, I can always compute I can initiate D0 array and then I can compute Dn minus 1 array. That I can do for all graphs. They just need the input weights of the graph, other than that you do not need anything. So, if G is an arbitrary graph, first compute Dn minus 1 array of values, that is you are going to compute Dn minus 1 V for all V belonging to V. For all vertices you are going to compute this. Okay? Now this is what you are going to do next. For each U V belong to E, if Dn minus 1 of V is greater than Dn minus 1 U plus weight of uv, if this happens for a particular edge, return, that is terminate the program, return the message G has a negative cycle. Because G has a negative cycle, just terminate with the report that G has a negative cycle, that is it. If this happens even for one edge, when you encounter just one edge, you do this. So at the encountering of the first edge satisfying this condition, you terminate the program and report that G has a negative edge. Suppose this has not happened for any edge, that means you will execute the step 2, but you will not return anything, because this condition will fail. Dn minus 1v will be less than or equal to Dn minus 1u plus w for all edges. Now you know that G has no negative cycle. Since G has no negative cycle, you know that Dn minus 1 is carrying the correct values. So step 3, return Dn minus 1 v and previous of v for all v belonging to v. So you will execute step 3, only step 2 does not return anything. If step 2 returns, the control is returned, the code is terminated, you will never go to step 3. So if step 2 returns, you are terminating with a message that G has a negative cycle. Notice that I am not returning the D values, P values, nothing. I am only reporting that G has a negative cycle. That is because if G has a negative cycle, all the computation I have done of course, they are useless. The D values are not shortest path weights at all. So I am not going to return any of them. Okay. So this is the complete Bellman Ford algorithm. The Bellman Ford algorithm, if G has no negative cycle, returns the shortest path weights. If G has a negative cycle, it reports that it has indeed a negative cycle. Okay. Very clever and nice algorithm. The complexity is very easy to determine. Okay. Complexity of Bellman Ford algorithm. It is very simple. There are n minus 1 iteration. In each iteration you are working on all edges. On behalf of each edge you do one comparison and one assignment. Therefore, the complexity is clearly n minus 1 times m. There are n minus 1 iterations. If the G is arbitrary, after finding d n minus 1 in n minus 1 iterations, you make one more pass on all the edges, that will be another m. Therefore, the complexity is order n m. This is to check the, this is to compute d n minus 1 array. This is to check if G has a negative cycle. Therefore, you are able to solve the problem in order n m time. Single source shortest path problem on an arbitrary graph is solved in the following manner. Okay? If the graph has no negative cycles, it will give the answer. This will not give any answer if the graph has got negative cycle, because if the graph has negative cycle, computing the shortest path distance and other things, we cannot use this approach. Why we cannot use this approach? All this approach is based on Bellman equation. Bellman equations are valid only when the graph has no negative cycles. If the graph has no negative cycle, Bellman equation itself does not hold good, and none of these steps would make any sense, and hence the value you have makes no sense. That is the reason why for a graph that has a negative cycle, I simply report that G has a negative cycle and do not return any values. But if I am convinced, if I am confirmed that G has no negative cycle, then the Dn values will be returned. Okay? This completes the discussions related to Bellman Ford algorithm. Thank you.